So just to remind ourselves, we had what we called the central limit theorem, which had some key statements. And it was talking about two sampling distributions, one being the sum and one being the mean. So we get a sample of a certain size, we find the sum of all the values, or we find the mean of all the values. We do that lots and lots of times, so we build up a distribution of sums or a distribution of means, and we find in both cases that if n is large enough, if the sample of if my sample size is large enough, I'll get something that approximates a normal distribution. And that's regardless of the distribution of the population. Now, the mean of the sums is just the sample size times the mean of my original population. The standard deviation of sums is the square root of my sample size times by the standard deviation of my original population. The mean of my means is constant, so regardless of my sample size, it should always be the same and is equal to the population mean, provided that my sample size is large enough to mean that the central limit theorem applies. Okay, and the standard deviation of my means is the standard deviation of the original population divided by the square root of n, where n is my sample size. And if we increase our sample size, the approximation of normality increases. In other words, it becomes more normal. Standard deviation of sums increases, the standard deviation of the means decrease. And then we looked at, well, how large does it need to be for the central limit theorem to apply? And I made emphasis that the textbook says n greater than or equal to 30. While that's not wrong, it is not what our course uses. Okay? We have to assess it based on a distribution that we're given and basically say, does it work? Okay, all right, and then we're looking at how we can use these results in a whole bunch of different questions. So we got up to here and we're looking at Dow has an MP3 player that uses one AAA battery. When a certain brand is used, the playing time varies according to a distribution with a mean of 10.85 and a standard deviation of 1.35. They're sold in packets containing a different number of batteries. Suppose he buys a packet containing n batteries and each battery is used in the MP3 player until it's exhausted. Then they show us two histograms below representing the distribution of n, the means of samples of 4 and the means of samples of 15. And we see that this one must be x bar 15 for two reasons. Firstly, it's a better approximation to normality. Secondly, it's got a smaller standard deviation. And then it says, is n equal 20 sufficiently large in this case? So this is the point that I was making where we don't just use n greater than or equal to 30. This is definitely less than 30. But here, this is x bar 15, this one here, and that's pretty normal. That can be said to be approximately normal. And so any sample size more than that is going to be even more normal. And so we can say that n equals 20 is normal enough to apply the central limit theorem. And that's where we got up to last time. So they say, show that x bar 20 has a mean of 10.85 and a standard deviation of 0.302 hours. So, mu, I'm going in black, mu of x bar 20 is equal to mu of x. And we saw that mu of x was just 10.85. So mu of x bar 20 is just mu of x, which is 10.85 hours. And sigma of x bar 20 is equal to sigma of x divided by the square root of n. Now, if I just jump back to the question, just to remind myself of the standard deviation, it was 1.35. So it's 1.35 divided by the square root of 20, and we could go through and calculate that, but that's just going to be 0.302 hours. Okay, find an approximate value for the probability that the mean of 20 values is going to be greater than or equal to 10. So here, we're using this idea that x bar 20 is normally distributed with a mean of 10.85 and a standard deviation of 0.302. Now, this is a past exam question, and note one very important thing. If you were unable to complete the previous question, you can still do this question. Okay, they've given you the key results that you need down here. So even though you may not be able to find the mean or the standard deviation, you can still find this probability because you've been given the key results from here. They will supply you with some key information in some cases where you won't be able to find it, or you may not be able to find it, and you'll be able to use that in future parts of the question. So just always be on the lookout for that you may be given what you need. So let's then just say the probability that x bar 20 is greater than or equal to 10 is equal to, well, if I go to my calculator, so everybody get your calculators out. This is a normal distribution calculation because remember, we've said that x bar 20, the distribution of x bar 20 approximates a normal distribution. So we just use NCD. So it's distribution, normal, NCD. By the way, if anybody is wondering for either this test or the next test if NPD is ever useful, no it isn't. Okay, we never use NPD. Okay, so NCD data, the variable, we're going greater than 10, so our lower value is going to be 10, our upper value is going to be the highest thing the calculator can handle, which is 1e to the 99. Sigma is 0.302, and our mean is 10.85. Okay, alright, and if I go through and calculate that, it's 0.998. Just watch on the last decimal place. If you're going to 3 decimal places or 3 significant figures, just make sure that you actually round correctly. It's easy to read that and just say 0.997. That's actually 0.998, so make sure you round correctly. Say 0.998. Okay, when a normal distribution is used to approximate x bar 4, the probability that x bar 4 is greater than 12.5 is 0.00725. Is this too small, too large, or about right in comparison with the exact value of the probability? Explaining your answer referring to the histogram of x bar 4. This is the histogram of x bar 4. Notice it has a lot of area under this tail. It's skewed. So if I draw a normal distribution, it looks like that. It's symmetrical on both sides, but this is our normal. If I draw the histogram of x bar 4, it's probably going to look something like this, with more area under the tail out here. So this is for x bar 4. So what that means is, if we use a normal distribution, it's actually going to be too small. Notice the normal distribution goes a lot closer to the x-axis than the distribution of x bar 4 does. So when 0.00725 is too small with compared to the right value for the probability. And that's because x bar 4 is skewed to the right, and so has more area under the right table, the right tail, compared to the normal. Now, in considering this, we should also just consider the value, like why am I talking about the right tail? Well, here, this mean is about 10.85, which then means that 12.5 is going to be, which is the value we're considering, is going to very approximately be about there. So that's 12.5 there. Then under the x bar 4 distribution, I've got all this extra area compared to the normal distribution. Now, if we just approximate this to be a normal distribution, it's just going to give me that area, but x bar 4 has a lot more area under that. So the normal distribution is not really appropriate for a value like this. Probably if you're doing the area less than some value down here, the values would probably be comparable, probably be about valid. But in this case, it's not, because we're going the other side. Okay, all right. Dale is going on a long driving holiday. He decides to take enough batteries to give a probability of 90% or greater of being able to use his MP3 player for more than 200 hours. Show that 18 batteries will not be enough. Okay, all right. If we want the total running time of 18 batteries, what are we going to use? Sums or means? Yep, sums. We're actually going to jump into a sum distribution. Now, to show that 18 batteries is not enough, it's going to have to be the sum of 18, of a sample of 18. And we can say that's normally distributed with a mean of 18 times 10.85 and a standard deviation of the square root of 18 times by 1 point, remind myself of the value, 1.35. Okay, so showing that 18 batteries will not be enough. Well, we want the probability that the sum of 18 is greater than 200. Now, notice it says in the question for more than 200 hours. So that's why I'm putting a strictly greater than sign. If you do greater than or equal to 200, well, the calculation in the calculator makes no difference for a continuous rounding variable. So it doesn't really matter, but it's a better idea to be consistent with the question. So the probability of the sum of 18 is greater than 200. Well, to work that out, we need to go back to our calculator. So if I go back to my calculator, I'm going greater than 200. So I'm going to put my lower value in as 200, and my upper value is going to stay as the highest thing the calculator can handle. My standard deviation now is 1.35 times by the square root of 18. And my standard, my mean is 10.85 times by our sample size, which is 18. Okay, alright, and enter, I get 0.206. Notice I'm rounding there. So it's 0.206, which is 20.6%, which is definitely less than 90%. Now it doesn't seem like that's the right value. If we're going to get all the way up to 90%, seems like it's too small, but let's just keep going through with it. And then it says, show that a minimum of 20 batteries will be enough. If it's a minimum of 20 being enough, that means that 19 must be too small. So to show that a minimum of 20 is actually enough, we need to show that 19 is not enough. So x bar 19 is normally distributed with a mean of 19 times 10.85 and a standard deviation of the square root of 19 plus 1.35. So then the probability that x bar 19 is greater than 200 is equal to, we're going to have to come back to our calculator. I'm going to keep 201e to the 99, but now it's going to be the square root of 19. I probably should pop that in brackets, times by 1.35, and then it's going to be 10.85 times by 19, and that gives me 0.852. We see that it suddenly rocketed up. That's a massive jump, but that's okay because we're dealing with big numbers. So, and our standard deviation is getting larger every time we do it. So this is 0.852 or 85.2%, which is a lot closer, but it's still less than 90%. So we want this probability more than 90%. Now we could assume that it is going to be 20, but we've got to go through and actually find the value to verify that. So then we're going to go 1.35 times by square root of 20, and then it's going to be 20 times by 10.85, and that's 0.998. So then x bar 20, just to finish it off and communicate, is going to be 20 times 10.85 root 20 times 1.35 is the standard deviation. So then the probability that x bar 20 is greater than 200 is 0.998, which is 99.8%, which is greater than 90%. Therefore, 20 batteries is enough. Now notice with this question, when you're changing your sample size, a lot changes, okay? Come to the question in a sec. Both your mean and your standard deviation of the distribution you're working in changes, okay? The value that we're considering doesn't change, but your mean and your standard deviation change in all situations, so you've got to be careful to follow through with the effects of changing your sample size. Mean changes, standard deviation changes. Mean changes, standard deviation changes. It's not just as simple as one of them changing. Here both change. Yep. Well, I was working with the sum, wasn't I? Should be. So I've just got the wrong notation there. So here, this mean and this standard deviation are both for the distribution of sums. So I was just using the wrong notation. So that's S19, S19, S20, and S20. Yep, so it's not means and sums. Thanks for pointing that out. Okay, all right. Okay, question 3. The weight of individual veggie sausages varies. Let W represent the weight of a randomly selected veggie sausage. W can be modeled by a normal distribution with a mean of 55 and a standard deviation of 7. Okay, alright. Now this is actually a question from my year. So I did this question in my studies exam. So what is the probability that a randomly selected veggie sausage will have a weight of less than 50 grams? Well, W is a normal distribution, so we can use normal distribution calculations. So this is the probability that W is less than 50, and we know that W is normally distributed with a mean of 55 and a standard deviation of 7. So going back to my calculator, we want less than 50. So our lower value is going to be 1e to the 99, that's the lowest. Negative 1e to the 99, then it's going to be 50. Standard deviation is 7, and then the mean is 55. And we get 0.238. So that's equal to 0.238. Okay, let S6 represent the sum weight of 6 randomly selected veggie sausages. State the distribution of S6. Well, S6 is normally distributed. I know that it's normal because W is normal. We're getting our samples from something that is already normal, so it doesn't matter the sample size. Every sample, the distribution of sums and means of any sample size will be normal because W is normal. So I can say it's normally distributed with a mean of 55. It'll be the same as W, and then 7 over the square root of 6. So I want everybody to calculate our standard deviation. 7 divided by the square root of 6. What decimal does that give us? Alright. 2.86. Okay, alright. Calculate the probability that S6 is less than or equal to 300 to verify that the probability that S6 is less than 300 is equal to 0.04. Okay, so the probability that S6 is less than or equal to 300, we know it's normal, so this is going to be an NCD calculation. Jumping back, less than 300. So our lower value will stay as it is. Our standard deviation is 7 divided by square root of 6, and the mean will stay as 55. Okay, and if I go through and calculate that, yep, 1, which is definitely not what I've done. Okay, let's think about it again. Alright, so probability that the sum is less than or equal to 300. What have I done? What have I done? Yep. No, it's not, is it? What is it? Yes, that. Okay, alright. So what's 6 times 55? 6 times 55. And root 6 times 7. Sorry? No? Root 6 times 7. 17, or round that to 17.2, but 17.15. Okay, now we're ready. So, 7 times square root of 6, and it's 55 times 6. Okay, alright, 0.0276. Did I? Let's try that one more time. There we go. 0.0401. Okay. So it's 0.0401, which is approximately equal to, or it is equal to 0.04 to do decimal places. Okay. All right. Now, veggie sausages are sold in packets labelled as containing 6 sausages with a net weight of 300 grams. Suppose that 6 veggie sausages are randomly selected during the process. If the combined weight of the veggie sausages is less than or equal to 300 grams, a 7th sausage is added to the packet. Outline the reason why. The mean of 6 of them, less than 50, is the probability that a 7th sausage will be added. So, the probability that the mean of 6 of them being less than or equal to 50 is actually equal to the probability that the sum of 6 is less than or equal to 300. Because if the mean is 6, if the mean of 6 is less than or equal to 50, the total sum will be 6 times 50, which equals 300 or less. Hence, probabilities are the same, and the probability that S6 is less than or equal to 300 is the probability that null sausage is needed. 7th one. So you can actually do it 2 ways. So this probability here, the S6, the sum of 6 is less than or equal to 300, will be the same probability that the mean of the 6 will be less than or equal to 50. It's an equivalent.